Okay, so we have been, via the principle of equivalence, have been thinking about curved space as a way of getting to curved space-time. And so we eventually want to get at an understanding of the motion of objects in curved space-time. And in particular, we want to start by understanding, the equivalent in space-time of objects that move under no forces. So what does it mean to move with a constant velocity, right? Because ma equals f, so this means that ma equals 0, and so we want to understand the motion that is associated with an unchanging velocity. So this kind of thing, if we write velocity in terms of Cartesian coordinates, so we have an x component, let's say we're in the xy plane, plus the y component j hat, then in a flat space, and we'll generalize these ideas to curved space, and then to, of course, curved space-time. But in a flat space, there's no ambiguity about, if this is the y direction, right, then that's the j hat, and if this is the x direction, that's the I hat, and of course that direction is unchanged. So on my sheet of paper over here, at this point, the y direction is still, there's nothing confusing about trying to figure out the y direction here. This thing points in the same direction as this one. They're parallel, and the same is true about this object. So I can imagine, traveling or considering many different points, and drawing the x and y directions, these basis vectors, and there is a sense, maybe we'll draw one here, and maybe here again, and that's it. There is a sense in which there is, all I need to do really is to say something like this, y and x. There's a global notion of the y direction and the x direction. There's a global notion of the vector that's pointing to the right and downwards, because the space is flat. But on a curved surface, this is not true, and these ideas will translate to curved space-time as well. So on a curved surface, so let's just write this. There's a global notion of x and y directions. And of course, all this applies to x, y, and z. But for simplicity, we want to explore this in two-dimensional spaces. On a curved surface, so on a curved surface, this all falls apart. So let's consider a sphere. So let me try to draw a half of a hemisphere. So this is the North Pole, and this is the equator. Let's see. And this is sort of 90 degrees here. Not the greatest drawing, but whatever. So let's say I try to put a coordinate system, XY coordinate system, at different points. So I'm at the North Pole, and so I decide that the Y direction is to the right. That's my J hat. And my X direction is out of the page right here. So it's X and Y. And now I sort of follow what I did here. I'm trying to keep these things parallel. So the Y direction continues to point to the right. And so here it means that as I'm moving away from here, I'm going to continue to point. I'm on the surface of the sphere. I'm going to continue to point that way. So my Y direction, my J hat looks like that there. And my X direction is pointing out of the page, and I continue this all the way until I get to down here, and then the J direction is pointing, the Y direction is downwards, and the X direction is still out. And then I continue to do this as I'm going around here, and my J hat is that way, and my I hat is to the left, tangent to the equator. And then when I get here, that continues to be true. But notice that if I start to go up this way, then my I hat is like that, my J hat is like this. And when I get to the North Pole, my I hat is to the left, whereas initially it was out of the page, and so it's rotated by 90 degrees. Same is true for the J hat. The J hat that's downwards here, and at this point then points outwards, because I keep trying to keep it parallel to itself as I'm moving here. So everything has rotated, the coordinate system has rotated there by 90 degrees. And if I continue thinking about this along here, if I don't go up there, J hat and I hat, and then when I'm doing 180 degrees here, I'm halfway around the circle, on the equator here, I come up this way, then my J hat is downward here, and my I hat is into the page. And so when I get here, my J hat will be 180 degrees, and so is my I hat, because now the I hat is into the page. So it depends on the path that you're following. There is no global, so no global notion of the X and Y directions. And so we're going to need, we basically need to consider how these unit vectors here are changing in the space, and by extension in space-time. And so when we take derivatives of vectors and other objects, we're going to have to take derivatives of all of these objects, and these are not going to be just quantities that don't change as we're moving in space. They will actually change, and these are the kinds of mathematical objects that we need to consider.